they make no errors. The only effect they can have is possibly slowing down the convergence. So you can have a system running very efficiently, the network changes, it's unstable, convergence slows down. When the network becomes stable again, everything speeds up again and runs normally again. And the blue nodes is where state can disappear. So that's a little bit harder because the node state is important. But as long as there's one node with the state that you need at any instant, that's the only condition, everything will work fine. Okay? So this all seems very nice. So convergent computation seems like a nice idea, but there's still some big rabbits I have to pull out of the hat. Will it work? Okay, it's a good question. Can we implement this approach efficiently? Is it easy to program? What does the programmer have to learn to program in this kind of environment? Actually, it is easy, and we can implement efficiently. And in fact, pedagogically, I'm presenting convergent computation, but actually, we came to it in sort of around that way when we're looking at synchronization-free programming. So this actually, it's not completely new. It's actually used already today by many companies. Many of you are already using it. So all the logos that you see there are using CRDTs, which are basically just convergent data structures. But we want to generalize that to actually do computation, full-fledged, arbitrary computation. So that's really what we want to do. We want to move from just single data structures that are convergent to arbitrary computation. So let me cut to the quick immediately, and let me show you how to program in our system, LASP. So our LASP prototype is able to do a number of convergent computations. So here's a simple LASP program. So basically, in this program, the two orange balls are just variables, okay? S1 is a set, S2 is a set, and they're connected using a map process, which does a mapping of the set elements from S1 to S2. So for example, the map in this example, so this syntax is very, very similar to the syntax of our current LASP library written in Erlang. So you declare a set, the initial value is 1, 2, 3. The mapping is going to go from x to x times 2, very simple mapping, okay? So this is very straightforward, right? Doesn't look very hard to program, and it's not. So basically, in general, you have a whole graph of these data structures. You have the data structures, the processes connecting them. The map operation here is active. It's an active process. And if you add one element to S1, then the map will activate and add an element to S2. It's like functional data flow programming. This seems very simple, right? Actually, when you do this, you've got it all. You've got convergent computation the way I just mentioned a few minutes ago. So the data structures are fault tolerant. Okay, they're replicated. So this is transparent. In the program you just saw, they're replicated and consistent. But they're also convergent, which means that they have all the good failure properties that I mentioned before. And the new thing we add in the research project is that the programs, the LASP programs, are also fault tolerant and convergent. Not just the single data structure, but the whole program has this property. So it seems very simple, but actually there's a lot of stuff, clever things going on under the hood. So I'm going to give you all of the major intuitions of that so that you can understand how it works. So here's another program, a little bigger. So we've written bigger programs, of course. Here's a more complicated example. So we have, it's called add counter. You have a series of adds. You have a series of contracts. And basically, when on a mobile phone you see an ad, when all the users see the ads, the companies putting the ads pay the application, the game, or whatever, depending on the number of views of the ads. So 1 million views or 100,000 views, depending on geography. So this does that. So basically the ovals here are sets also, but you can consider them to be like tables and databases. The processes here, product and filter, are combining it. So this is a part of the add counter, just to show you the kind of program you can do. But today I don't want to just do programming tutorial. I want to show how it really works. I want to show what's under the hood. So if you want to experiment with LASP though, please feel free, try it out. We're also looking for developers. If you think it's interesting, please get in touch with us. So there's documentation, there's a documentation site, and there's a repository with the code, and we even have a logo, so it must be good, right? So now let me go and give you a little bit of theory. How does it actually work? What's under the hood? First, I want to explain what is this convergent idea more precisely. And actually, I'm going to talk about convergent consistency. And then I'll talk about convergent data structures. So basically, it starts with CRDTs. You may have heard of CRDTs. And then it goes on to combine the CRDTs to make programs. So CRDTs are convergent, and LASP programs are convergent. So I will show you two theorems. So we've proved that formally. Since we're academics, we have to prove theorems once in a while. And then I'll show you also the hybrid gossip, the communication layer that makes the whole thing work. Okay, but let me say first a little bit convergent consistency. How do we see this? So the idea is we want distributed programs, distributed systems, to be both easy to program and efficient to execute on the standard hostile environments that we all know and love or hate or whatever. So this actually is a kind of holy grail. It's hard to combine those two. So strong consistency, or what is known as linearizability formally, means there's a total order of operations. It's basically like running a sequential program. It's actually easy to program with, something that we all learned. There's another extreme called eventual consistency, where you can do operations, they execute asynchronously, you can have many operations in the system at the same time, executing concurrently, and they will all eventually complete. But this is hard to program because these operations, they might conflict with each other. But it's efficient, okay, because of the asynchronicity, and you don't have to do any global synchronization, which is you do have to do for linearizability. So the question, can we get the best of both worlds? That's what we want to do. So convergent consistency, the third one, we aim for that, okay? We're aiming for the grail. And I'm going to explain a little bit the thinking that is behind that. So let me start back to basics on distributed systems. So a distributed system, collection of network nodes that in some sense behaves like it's one system. And what that means is there's something called a consistency model that gives the properties of the whole system, okay, in red here. And in order to make this work, we need some kind of an algorithm. The nodes have to coordinate with each other according to some rules that are well defined. And this is called the synchronization algorithm. So we need a synchronization algorithm to get a consistency model. So for example, in my distributed systems course, I talk about reliable broadcast algorithm, and it has this property called all or none. Either all correct nodes deliver the message or none do. That's a global property. So that I make it in red there. That's the consistency model for the reliable broadcast algorithm. Okay, now let's see how can we push this. What do we want to do here? We want the consistency model to be as strong as possible, like linearizability or something like that. But on the other hand, we want the synchronization algorithm to be as weak as possible because synchronization is expensive. We don't really want to have Paxos running everywhere, okay, or barrier synchronizations, whatever. Not scalable, it's expensive, and so on. So how can we marry these two tensions? Well, one particular example, extreme case. The weakest possible synchronization algorithm is no synchronization at all, where the nodes are just doing whatever they want without caring about the other nodes. This enforces no consistency model, or empty consistency model, which is very hard to program, okay? There's no abstraction, there's nothing. So this doesn't work. We need something more. Well, it turns out that there's a very interesting sweet spot in this trade-off. It's called strong eventual consistency. And the idea is the following. If I have a data structure with n replicas, and I'm doing operations, distributed data structure, the replicas are supposed to be consistent. Using Paxos, replicated state machine, I would have to do Paxos after every operation. Here, no. Strong eventual consistency says that two replicas that have received the same n updates in any order will have equivalent state. So it doesn't matter if the updates come in a different order or whatever. As soon as they get the same updates, they have the same state. That's a very weak model, okay? And the only synchronization we need to do that is eventual communication, replica to replica. If I send an update to one replica, eventually it has to propagate to the others. So the only synchronization algorithm is replica to replica communication. Now, this model seems to be very weak, strong eventual consistency. It's actually amazingly powerful, and discovering the power of this approach, this property, is what led to this whole project, and is what led to the EU giving us loads of money for making it work, okay? So the power of it, you can do functional programming, something that looks very much like functional programming. You can support non-determinism. You can support non-monotonicity, so data structures where you add and remove. So even though it's convergent, that's okay. It supports that. Also, you can implement it efficiently and resiliently. It obeys all of the good properties of failure. So coming back to the three consistency models, strong consistency, linearizability, very often it's expensive, especially if you want to scale it up, but easy to program. Eventual consistency, many operations are in flight at the same time, very efficient, but they can conflict. And if they conflict, you have to fix it, okay? So the more operations you have, the harder it gets, and they can conflict at different points during their execution, so on, hard to program because of these conflicts. So convergent consistency is just eventual consistency plus this extra property, strong eventual consistency. And you saw the last program I just showed you. That one is giving you this the same efficiency as eventual consistency, almost. There's a few small overheads. There's some metadata. There's the replica-to-replica communication, which can be done kind of offline. But within some fairly small constant factor, it's as efficient as eventual consistency, and it's as efficient in terms of latency. So we can't get the CAP theorem. We can't have consistency, availability, partition tolerance at the same time. But what we are giving you now is availability, partition tolerance, and convergent consistency, okay? So let me now talk about convergent data structures. So I'm going to talk to you about CRDTs and how they make things convergent. So probably many of you have already heard or used CRDTs, right? How many of you have heard about CRDTs? A whole bunch. So, and there's been, so my PhD student, Christopher Mickeljohn, has been doing lots of talking about CRDTs, so you've probably talked to him maybe. But he hasn't been giving so many theorems, so I'll give you a few theorems. First of all, a definition. So I'll give you some Greek letters and some theorems. So a CRDT is an example of a convergent data structure. And I'm going to define what's called a state-based CRDT. There are different forms. It's very general. This is a particular one which is pretty nice, but there's others. So it's a triple. You first have a configuration. So n replicas with a state on each replica. That's very straightforward. And there's one difference, though. The state is not just some random value. It's an element of what's called a join semilattice. So this is the magic that makes the CRDTs work. So I'll explain in a minute what this join semilattice is and what it gives you. The CRDT also has a query function. So for example, in a set, you get the value of the set. And it has a mutator, basically an update write, basically read and write. Okay? And periodically, the replicas talk to each other, and they merge their respective states. So this, again, is where the join semilattice comes in. The mutator will inflate the state. Basically, it moves up the lattice, and the join operation will merge two states on the lattice, also moving up on the lattice. So because of this, this structure is convergent. Proving that completely formally takes a little bit of effort, but intuitively it's pretty clear. The mutator is always making the value moving up, and the join operation is always merging values. So when all replicas see all updates, they've all moved up to the same value, okay? So a little bit more about the join semilattice, which is the magic ingredient that makes the state-based CRDT work. So a join semilattice is actually not a very complicated thing. It's two things. It's a partial order, so basically nodes with arrows between them going in a particular direction. And the real trick is that there's a least upper bound operation. So here's in the slide, there's an example of a lattice. So if you take the two lattice elements A and B, and you do the join, you basically find the least element that basically covers both of these, which is C in this case. So C is the join of A and B. So you're essentially generalizing. So in the lattice, you're always moving up. So you're always generalizing information from previous information. This seems kind of limiting, right? That you're always moving up. It's always monotonic. How can you build a data structure where you remove things with something like that? Actually, it's pretty straightforward. You just have to remember that the semi-lattice here doesn't have to be the actual data. It just represents the data. So you just need another level of abstraction. So I'm going to show you one CRDT in this talk. There's actually many, many different ones, very clever ones, using vector clocks, using all kinds of ideas to be very smart. But I'm just going to show you one to show you the basic idea, how it works. It's called an observed remove set. It's just a set of elements where you can add and remove elements. That's basically what it is. But the trick is, how do you represent removing elements when all the operations are moving up on the lattice? So I'll explain it. First, the specification. How does this set work? Because it's a distributed data structure. Well, if you do sequential adds and removes, it has exactly the same behavior as a sequential set. But in the distributed system, you have to generalize the specification because you can do concurrent adds and removes. So basically, a remove will remove all of the elements that were added that are causally visible. So it depends on the causal history. And concurrent adds and removes, the add wins. Okay, so it's also called add wins set. So how does this work? Well, the idea is that internal to this OR set, for each element, we add some metadata, which represents whether it's been added or removed, and is cleverly designed so that it always moves up on the lattice. So we basically have unique tags for every element. So here's an example execution. So we have three replicas, R1, R2, R3. So time goes from left to right, and the set is initially empty. So let's say on R1 I do an add of element 1. What I will do inside the OR set is I create a triple. So the first part of the triple is the element. The second is a unique constant that identifies that particular add. So each time you add, you have to create a unique constant. And the third is a set of which elements have been, whether the element has been removed or not. So it starts by 1A empty. If you look on the top, it means that the element 1 has been added. R3 also I add 1. Here I have 1B empty, so another constant B. Okay. Assume now in R3 I remove 1. So the remove operation, what it does is it takes the third element of the triple and sets it equal to the second. And what that means basically is for each triple where you have an element and set of add constants, set of remove constants, the element is in the set if the set of add constants is strictly a superset of the set of removes. If it's equal, then the element is not. And now execution goes on. We also have the arrows, these sort of blue arrows going between the replicas. These are the periodic merge operations. So basically the synchronization between the replicas. So For example, moving the first arrow on the left, if you take 1b empty and you move it, then R2 will have 1b empty. The second arrow to the left, that goes from R3 to R1, you take 1b B and 1a empty. You take the union of the A and the R, that gives you 1AB and B, which means that 1 is still in the set. If you keep doing this, when all information propagates at the end, it turns out that the add 1 done in R1 has no remove. So the add 1 in R3 has been removed, but add 1 in the top has not been removed. So at the end, all three replicas agree that 1 is in the set. So it's consistent. Okay? It obeys strong eventual consistency. With the same operations, when the information is propagated, they are consistent. Notice we don't need consensus to do that. And in fact, if you look carefully, you see, it's written in red on the bottom in the slide, that the triples are always moving up in the lattice. Okay, so you can see the trick, how it works. Okay, so you can actually prove a theorem. A state-based CRDT is convergent. It satisfies strong eventual consistency. So we assume that an update delivered at some correct replica will eventually be propagated to all the replicas. This is an important assumption. This is the synchronization model that we're assuming. And if all correct replicas have delivered the same update, so basically the update is in their causal history, then they have the same value. And you can prove the theorem, and there's an INRIA research report. The reference is on the slide, which I recommend you read if you want to understand more. And you can go farther, and not just single CRDTs, but whole LASP programs now, like the programs I showed you. These easy-to-write programs actually have a very strong property. They all satisfy strong eventual consistency. So what is the fault model for this theorem? So basically, we're assuming crash stop, and at least one replica is always correct at any instant. That's the assumption that makes this theorem true. And a simple LASP program is basically just an acyclic graph of data structures and processes. Of course, that's very trivial kind of programmer. So far, we don't have loops yet. That's pretty bad, right? So we're working on it. Things are coming. But it requires kind of clever metadata computation. So this model, we're generalizing it. But for the simple LASP program, we've proved that it also satisfies convergent consistency, strong eventual consistency property. And this also, there's a paper in a conference called PPDP 2015, where you can see the proof and you can really understand what's going on. Okay, so that's about the LASP programs. Let me tell you something about the communication. So our system has two layers. It has a convergent computation layer, but it also, the nodes need to communicate in these dynamic edge networks. So how does that work? Well, basically, we use hybrid gossip algorithms. These are really very, very useful and clever. So here's a typical one called plum tree, which is used in React, by the way, written in Erlang. So the system has two layers. You have a spanning tree, that's the bottom layer in the slide there, where the nodes are connected, and this spanning tree lets you do broadcast. So plum tree is an epidemic broadcast algorithm, which Jonas mentioned this morning. Thank you, Jonas. And on top of that, you have a resilient repair using gossip. These two together are a really nice sweet spot, okay? The lower layer, the spanning tree, gives you very efficient broadcast, but it's fragile. Anything changes in the network, a node crashes, the spanning tree is broken and it doesn't work. But no problem, the gossip layer on top is resilient and will repair it. It observes, using gossiping, it observes, each node observes its neighbors, and if there's a problem with connecting to a neighbor, it will adjust the spanning tree, and it will keep trying. Maybe the neighbor comes back again, well then it will rejoin again the spanning tree. So combining these two layers gives us an algorithm that is both efficient and resilient. It's a really nice sweet spot, okay? So I can recommend this kind of algorithm. It's really, really nice. The algorithm that we're using in LASP is actually a modification of another algorithm, another gossip algorithm called HyperView, which basically maintains connectivity. It's a membership protocol, but it maintains that all the nodes there's always a path between any two nodes. So it maintains connectivity, and in fact, if you look at the HyperView paper, they have measured almost 100, so 99 point some whatever, even when 90% of the nodes fail. That's pretty good. Huh? You can shoot them down, most of them, and it will still be connected. The ones that remain, the 10% that remain will still be connected. The way it works is that each node has an active view of nodes that it's connected to, and a passive view of nodes that it knows about. The active view is small, and there are regular communications going on to keep the system evolving, but you can't do that with very large sets. So the passive view is much larger. So if there's problems with any nodes in the active view, nodes come in from the passive. So there's a connection between the passive and the active view. And this way, HyperView maintains connectivity, even when huge number of crashes happen. So in LASP, we use this for the replica-to-replica state update. Okay, we guarantee connectivity. Okay, very good. Okay, I hope I didn't talk too fast because I'm almost at the end of my talk. Amazing. So I want to say where we're going in the future. What is the vision of this project? So a research project is always a combination of day-to-day implementation and so on, plus a long-term vision. So it's the long-term vision that's important. So let me explain a little bit where we're going. So convergent computation is not the end of the story. Paraphrasing Winston Churchill, maybe it's the end of the beginning, okay? But there's a lot more coming after. So today, we have convergent, consistent. We're doing convergent computation with CRDTs and LASP. The LASP language, which I explained to you in this talk, we also have a database based on CRDTs, a transactional database, sitting in a data center. We're not giving up completely. In fact, the world is going to have both. So that's also part of the project. The database is called Antidote. So I haven't presented it in this talk, but you can also find out about that. And we're applying it to edge computing. So we have a number of partners. So for example, Stritzinger, who maybe he's here and you saw his talk. So they have manufacturing systems, embedded systems in factories. So these systems can be very dynamic. Nodes can crash, but they have to keep working, and they have to do computation, online planning, for example. If part of the factory goes down, you want to replan the manufacturing. So it's a great example for us. So they're a partner in our project. We have other partners, sensor networks, community networks, also a company called Scality, where they want to have this big database. They want to push it to the edge with very complicated indexing. In fact, indexing data is 10 to 100 times bigger than the actual data, the indexing. So this requires computation to maintain. So they want to improve the user performance going to the edge. So that's what we're doing today. In fact, we're fairly ambitious. We want to take non-trivial computations that people would today, like a no-brainer, do on a database, and do them directly on the edge network. How can this work? Well, what we expect is that edge networks, they have different phases. They can be stable, unstable. There's usually some strong nodes, a bunch of weak nodes. Things are changing all the time. So as long as there's a few strong nodes, we hope to get similar efficiency to data center, because the system will reorganize itself so that it's running on those nodes mainly. If the network becomes flaky, then as I said in the beginning, there will be no errors. Computation may temporarily slow down, but as soon as the network stabilizes again, it will start running fast. And the programmer will be programming at a level that is what you see in the LASP code. So the programmer will not have to do any of that reorganization. That's what we're aiming for today. But tomorrow, so there's a nice example I want to show you. That's today. That seems pretty ambitious already. We're not sure it's going to work. But what's the ultimate goal? So here's an ultimate goal. In order to show you this ultimate goal, I'm going to tell you a story, a small story. Some of you have seen it already because Chris has already told this story in a talk. So here's the story. I call it Parable of the Car. So I have this nice car here. So it's a BMW, but there are other nice cars, but this is a BMW. And it's riding on a highway. And let's think about mechanically what's going on here. So there's this notion of friction in mechanical systems. And the tires grip the highway. And that's the only reason the car is moving forward. If there was ice, it wouldn't move at all. So the friction is essential. The car needs friction to grip the road to move forward. But on the other hand, the motor under the hood absolutely abhors friction. It doesn't want friction. Friction causes it to heat up and wear out. It wants zero friction. Well, actually, friction is like synchronization. Remember I told you that we want a weak synchronization model? That's what we want in the motor. Weak synchronization, no friction. But at the external world, you do need synchronization in the external world. So if you translate this now to a distributed system, you get something like this. I have a distributed computing system. There's services talking to each other. I have an interface putting information in. Information is coming out, the red arrows. There's an internal world to this system and an external world. Now, it seems that synchronization is only needed at the interface on the red arrows. So internally, the services, when they talk to each other, they don't need synchronization. They should be programmed using convergent computation. That's our idea. So synchronization is very similar to friction. Okay? It's needed to connect things in a strong way, sometimes in the real world, but very often for computations, you don't want it at all. So what this is moving toward is what we call synchronization-free services. So the whole system has a boundary, a synchronization boundary. Inside, all the services are using this weak synchronization, and the only time you need something strong, like consensus or barrier or whatever, is at the boundary, okay? And services live inside. Services are doing convergent computation. This means all services need a different kind of API. Current APIs are doing way too much synchronization. If two components, services, are talking to each other, you send a message, you wait for a reply, that's already a synchronization. It should all be asynchronous. It should all be convergent, so using metadata, being monotonic. That's kind of the dream. Probably we will not get it done in this project. That might be for a later project, if I can convince the EU to give more money after 2019. So, but that, in my view, is the ultimate dream of this approach. Okay, so let me conclude now. So I've explained to you what convergent consistency is and why we think it's a good idea, and how it's a consequence of programming with weak synchronization models, just replica-to-replica communication. I showed to you CRDTs, I showed to you LASP, which is a language we're building, and I gave you some URLs, and you're welcome to use it and complain if it's not doing enough. So we love to get your feedback. I'm actually also looking for a development engineer to help us work on that. So we're applying this to edge computing with our industrial partners. And the ultimate goal is, like in 50 years, in my view, all systems should be built to be synchronization free. So this is in the Lightcom project, which is a Horizon 2020, which is the current framework program of the European Union, 3-year project, and it's using LASP as antidote as starting points. And we hope we can make good progress. So you've seen just the beginning now. You've seen our prototype. We have to add a lot of things to make it work in practice, to make it be very general. We still have there's still some efficiency issues. There's some asynchronous garbage collection issues. There's some metadata issues. We have to worry about causality. We have to work about atomicity. I've not really told you a lot of the technical problems we have to solve, but there are many. But we're optimistic that we can solve many of them and that we can have a very good result. And that's all. Thank you.
Okay, questions? Oh, you knocked them dead.
I knocked them dead.
Yeah.
Boom, pow.
Eventually.
Eventually they will understand.
Yeah.
Convergent.
We'll get you out afterwards, right? Okay, thank you.
Question.
Oh, we have one. We have one. See? Eventually.
Do you know any real-world systems that uses CRDTs
Sorry, do I know?
Any real-world systems that uses CRDTs?
I showed you all those companies have real-world systems that use CRDTs. React is using CRDTs right now, and a number of the companies using React are using their CRDT library, like the Big Set library, for example. The company called Trifork has a database called FMK, which is basically providing the health care database for the whole country. It's in production, it's running right now. If you're a Danish citizen, you're using it, or a Danish pharmacist or hospital, it's using CRDTs. A company called Bet365 is using CRDTs. By the way, the ad counter example comes from Rovio, who is using React, okay, as part of Angry Birds, and so on and so on. So there's a pile. I don't know all of them, but there's a whole bunch. Probably some of you have more examples that I don't even know about.
Thank you.
Any more? Nope. They'll catch you later.
Okay, thanks.
Thank you.
Yeah.